we want to determine the values of x for which our series converges. So in the images, we saw that the series seemed to converge, at least pictorially. We could see that the approximation and the true function were very close together. So we'll just assume that it converged on those values. But is that always going to happen? Well, if you remember from earlier in this chapter, we learned about the ratio test. And the ratio test is going to be a great tool to help us answer this question, because it's going to allow us to figure out for what values of x we get convergence. So let's apply the ratio test on our series. And it's been a while since you've used it. So if you remember, we have to compute the limit as n goes to infinity of an plus 1 divided by an. And you may wonder, what is an in this case? Well, an is just the nth term of our series. So this right here, in our case, it just also has an x in it. This is an, the nth term in our series. Okay, so let's see what we get when we plug in n plus 1 and n into the terms of our series. So an plus 1 is 2 to the n plus 1 times x to the n plus 1 divided by n plus 1 factorial. And then we're going to divide that by an. So we're going to divide by 2 to the n, x to the n, divided by n factorial. All of that is in the denominator. And instead of dividing by a fraction, we can multiply by its reciprocal. So if I write that down, I still have my n plus 1 term, just copying that down. And then instead of dividing by the an term, I'm going to multiply by its reciprocal, so I have to flip that fraction. So I end up multiplying by n factorial divided by 2 to the n x to the n. And now we can simplify. So this is the first time that we are seeing an example like this. So but you may notice we have 2 to the n plus 1 in the numerator, and we have 2 to the n in the denominator. And then we have x to the n plus 1 in the numerator and x to the n in the denominator. And then we have n factorial over n plus 1 factorial. So let's group these together a little bit. So we have 2 to the n plus 1 over 2. And then we have x to the n plus 1 over x to the n. Those are going to simplify nicely. And then we have n factorial over n plus 1 factorial. And let's write down what those mean. So n factorial, that's 1 times 2 times 3 times all the way up to n. And n plus 1 factorial is 1 times 2 times 3 times, it starts out the same. Eventually we reach n, and then we have one more term, one more factor, n plus 1. So now you can see all these factors in the numerator and all these factors in the denominator, and lots of stuff is going to cancel. So here with the n factorial, almost everything is going to cancel, except in the numerator, well, we'll have a 1, and in the denominator we have n plus 1. And in the other terms, what do we have? We have 2 to the n plus 1 over 2 to the n. Oh, I forgot to write that down. I just fixed that. We have 2 to the n in the denominator. So we have one more 2 in the numerator than we have in the denominator. That simplifies simply as 2. And the same thing happens with the x to the n plus 1 over x to the n. That simplifies as x. And then we have 1 over n plus 1 left from the n factorial over n plus 1 factorial. We want to know what that limit is. Now, the limit only depends on n. N goes to infinity. So we can take everything that doesn't have an x, that doesn't have an n in it, and pull it outside of the limit. So this becomes 2 times x, but it's the absolute value. I have to keep that. The absolute value of x times the limit as n goes to infinity of 1 over n plus 1. I can drop the absolute value because n starts at 0 and goes off to infinity, so that will, the 1 over n plus 1 will always be positive anyway. And so now we can see, now we can let that limit go to take n to infinity, let n go to infinity, and that goes to 0. So this limit right here goes to 0, and it takes the 2 absolute value of x with it, so the whole thing goes to 0. Now, this is happening no matter what x is. This is true for all values of x. Now, what does it mean? This means that no matter what value of x is, the limit in the ratio test is equal to 0, and since r, the value in our ratio test, is 0, which is decidedly less than 1, for all values of x, we can conclude that this series converges for all values of x. Because if you remember, when this value from the ratio test is less than 1, we get convergence. And since we get 0 for all values of x, we get convergence of the series for all values of x. So we can conclude that this series converges for all values of x. And so going back, I'm going to scroll back to our image right here. So what seems to be happening for values between -1 and 1, that the Taylor polynomial gets closer and closer to the function, isn't just happening for values between -1 and 1. What this is telling us that no matter how far out we go, if we take enough terms, if we include enough terms in our Taylor series, we will get convergence for all values of x.